We present locate, localize and transfer object parts for weakly supervised affordance grounding. Weakly supervised affordance grounding aims to localize the action possibilities by using only image-level labels. Specifically, given an action, the task is to localize the actionable areas. For example, the blade of a knife for cutting, and the handle of a cup for holding. In this paper, we aim to learn affordance grounding from observation. We let the model observe human-object interaction images, where objects are being interacted. These images are called exocentric images that are used for learning. Specifically, at training stage, we input several exocentric images and one egocentric image. The problem setting is to learn where and how humans interact with objects, and then transfer the knowledge to the target egocentric image. During the learning process, only image-level affordance label is available. At inference, given an egocentric image and an affordance label, the model needs to localize the accurate affordance region. Previous work tackled this problem in a global and implicit learning manner. They pull close the global embeddings from two branches to perform knowledge transfer. However, we deem that this global information is too coarse to deliver affordance-specific information. Instead, we extract embeddings from the interaction regions, and select the prototype representing the object part, then we use this prototype as high-level pseudo-supervision to guide egocentric localization. We first find interaction areas and extract their feature embeddings. Then we learn to aggregate these embeddings into compact prototypes that indicate human, object part, and background. And we select the one representing the object part. Finally, we use the selected prototype to guide affordance grounding. Here we show the framework of locate, which transfers the knowledge from exocentric to egocentric branch in 3 steps. First, we utilize CAM to generate localization maps. Unlike vanilla CAM, we obtain these activation maps in the forward pass. For exocentric branch, we extract corresponding feature embeddings with high activation in the localization maps. Then, we propose PartSelect to automatically choose embeddings that represent object parts, and aggregate these embeddings into one prototype. Finally, we use the output from the selector to supervise the egocentric affordance grounding in a prototypical fashion. PartSelect leverages the part-aware features from DNO-VIT to distinguish which prototype stands for the object part. Specifically, we first perform k-means clustering to get k-compact prototypes from extracted exocentric embeddings. Then, we compute the cosine distance between each prototype and the egocentric deep features to get similarity maps. Owing to the fine-grained semantic information of DNO-VIT deep features, embeddings of the same object parts bear high similarity. Next, we aggregate the self-attention maps from the last layer of the DNO-VIT to generate a saliency map. And we introduce a metric termed part IOU to measure if a prototype carries object part information. Finally, PartSelect outputs the prototype with the largest score as the object part representation. Here we show the quantitative comparison to state-of-the-art. All experiments are conducted on the AGD20K dataset. It can be seen that locate outperforms state-of-the-art methods by a large margin in both seen and unseen settings. Besides, analyses on parameters and inference time indicates that locate has fewer parameters and is faster than most models. Compared to previous methods, we observe that locate can make more concentrated and accurate predictions. Especially for complex objects like bicycles and refrigerators, even in the unseen setting, our method can still locate the saddle of bicycles for riding, and the handle of refrigerators for opening. Here we show more visual results. In summary, we propose locate for weakly supervised affordance grounding. Unlike previous methods, locate achieves more localized part-level knowledge transfer to learn how humans interact with objects. And we use the learned knowledge to guide affordance grounding in an explicit reasoning manner. Locate achieves new state-of-the-art results, with fewer parameters and faster inference speed compared to existing methods. Thank you. Please see the paper for more details.